Hi, this is Johnny with Simpson Math. In today's video, or in this video, we're going to be talking about L'Hopital's rule and how to handle it. So at the beginning of the course, we introduced the concept of a limit. And a limit is just some number that the function is approaching. And we learned how to direct substitute to get a value, or if that didn't work, we had some strategies to rewrite the limit and find what that function was approaching. From there, we kind of used those limits to evaluate derivatives, or to find derivatives, using the definition of a derivative. Then we've moved on and we found a lot of derivative rules. And we've been on that topic for a while. But now we're going back to limits. And we're gonna learn about L'Hopital's rule. Basically, we have some limits that when we try direct substitution, we're not getting a number out, and our old strategies don't quite work. So L'Hopital's rule deals with when we do direct substitute and we come across certain situations. So those certain situations are what we call indeterminants. We don't know what they are. We cannot determine what that number is. So on the board over here, I've got a little, like a breakdown of them. And into this video, we're gonna be talking about how to handle difference, product, and ratio. And then we'll come back next time and talk about how to handle power indeterminants. But the first one, we got a difference indeterminant, infinity minus infinity. We don't know what that is. We cannot determine what that is. Some of us may want to jump straight to, oh, it must be zero because infinity minus infinity, they're the same thing. But we have to not think of infinity as a number. We have to think of infinity more as like a concept or this idea. So when I'm explaining it to students, I may say something like this. This first infinity is all the real numbers between 1 and 2. So on a number line, all the numbers between 1 and 2. So 1.2, 1.23, 1.2333, and so on and so forth. There's an infinite numbers. Maybe this infinity is all of the numbers between 1 and 3. So on the number line between 1 and 3, all of those numbers. So it's, and in fact, you may think, oh, well, that one's bigger or double the size of that one. But again, we can't think of infinity as a number. So we don't know, is one definitely bigger than the other? You could argue both. So basically, we just don't know. Maybe it depends on the situation. Same thing with the product, 0 times infinity. We're not sure quite what happens. 0 times any number is 0, but infinity is not a number. Same thing's true here. Infinity times a number should just continue to, be infinity. But what does that 0 do to infinity? And then ratio indeterminants, which is kind of like the main point today. If we have 0 divided by 0 or infinity divided by infinity, your instinct may say go to 1, but dividing by 0 is tricky. And then this is that idea of, is one bigger than the other? Infinity, we can't quite say. So these are very, we just don't know. In the next video, we'll talk about how to handle power indeterminants, but I can kind of address the indeterminants themselves. 1 to the infinite power, this is just saying 1 times 1 times 1 times 1 forever. And again, infinity is not a number, so this is not ever going to end. So I can't ever get to the end. I can't say, well, it should be 1, because 1 to the 10th power is still going to be 1. But we're talking about 1 to the universe, or some concept of infinity. And then 0 and infinity to the 0 power, we always said any non-zero number raised to the 0 power is 1. So if I had 5 to the 0 power, that's 1. But as soon as I put a base of 0 or a base of infinity, things change. I may need to write a video or something about how, like explaining this, but these come from the old exponent rules. It basically comes from division. So again, it's that idea of dividing by 0 and dividing by infinity, which are just too hard to do. They're situational. All right, So we're going to be dealing with limits today. We're going to try direct substitution, and we're going to be coming up today with these situations and how to handle them. So let me, I guess, just say what L'Hopital's rule is first, and then I'll try to explain it. All right. It says, L'Hopital's rule says, if I'm taking the limit of some function, let's say that's a q of x, the limit of some function, and I'm getting out, when I try direct substitution, a ratio indeterminate, 0 over 0, or some combination of infinity divided by infinity, a ratio indeterminate. I can't determine what it is. Then L'Hopital's rule says, what I can do is I can evaluate another limit, the limit as x approaches that same arbitrary value of a different function, where that different function is the derivative of the numerator divided by the derivative of the denominator. I'm not applying that derivative rule like the quotient rule. I'm not doing that. If I have this situation, I just take the derivative of the numerator separate from the derivative of the denominator. I can do that, says L'Hopital. And if I get a number, then the derivative of what I'm looking for will be that same value. Those limits will be equal. So the limit of the function will be equal to the limit of the function's numerator's derivative divided by the function's denominator's derivative. Yeah. All right, now L'Hopital's rule is very specific, and in today's lecture I may kind of gloss over that, but L'Hopital's rule, it's got a lot of specificities. It's very, it's hard to meet the requirements. So, first of all, f and g, the quotient, f and g, they've got to be continuous and differentiable functions. So it's got to be a differentiable function. I have to be able to take the derivative of f if I want to find f prime. So that means I've got to have this like interval of continuity. I can't have any kinks or any weird undefined points. And then of course, that bottom function, when I do take the derivative g prime, it can't be 0 because I can't be dividing by 0. So let's just jump straight into an example and I'll show you how this kind of plays out. All right, let's find the limit as x approaches 0 of, let's do something like sine of x over x. All right, I am evaluating the limit of this function as x approaches 0. This is not a derivative, this is a limit problem. So I try to first direct substitute. So I'm just trying direct substitution. That just means I plug in a 0. So wherever I have an x. So I have sine of 0 divided by 0. Well, I know sine of 0, I'm in a circle, sine of 0 is 0. So lo and behold, I get this 0 divided by 0. We call this a ratio indeterminate. I'm going to put a little asterisk here. This is just me telling myself that this is the L'Hopital situation. That means what I can do is approach, or I can evaluate a different limit. So instead of finding this, because that's indeterminate, what I'm going to do is evaluate the limit as x approaches 0 of same thing, but now what I'm going to do is I'm going to take the derivative of the numerator separate from the derivative of the denominator. We have a little symbol, I think it's kind of universal, where I'm going to apply L'Hopital's rule. So I put a little H or some sort of symbol to let me and whoever's reading your work know that you're applying L'Hopital's rule. So the limit I'm looking for is equal to another limit as x approaches that same value, but now I'm taking the derivative of the numerator. The derivative of sine is a positive cosine of x. The derivative of 1x is 1. Oh, so this is just the limit as x approaches 0 of cosine. different function. I'm evaluating a limit, so I'm going to try direct substitution again. And cosine of 0, well, that's going to be 1, positive 1. All right, we did it. So because the limit of their derivatives, top and bottom separately, is 1, then the derivative of what I was looking for is also 1. So I'm just rewriting it. The limit as x approaches 0 of my original function, sine of x over x, will also be going to 1. So I'll walk through that one more time. I had a limit problem of some function. I tried direct substitution. I got a ratio indeterminate, 0 divided by 0. So then I applied L'Hopital's rule. I just said, hey, that limit will be equal to this other limit where I take the derivative of the numerator and denominator separately. Then, with direct substitution, I got a value. The limit as x approaches 0 of that function is going to the number 1. So therefore, by L'Hopital's rule, my original function is also approaching 1. Let's go through that process again. Let's look at, oh, that looks crazy. Let's do it. Let's evaluate the limit as x approaches 2 pi of some quotient, where in the numerator I have x times sine of x plus x squared minus 4 pi squared all over x minus 2 pi. Looks kind of nasty. All right, but it's just a limit. So this is some function. If I were to graph it and look at the picture, I want to know what is the function doing as x approaches 2 pi. In fact, you could plug this into Desmos and probably just see what it's approaching. But I'm going to show some calculus. I'm going to try direct substitution. So I'm just going to plug in 2 pi wherever I see the variable x. So now I have 2 pi times sine of 2 pi plus 2 pi being squared minus 4 pi squared all over 2 pi minus 2 pi. Oh yeah, I can already see a 0 in the denominator. Now I just have to truly have a 0 in the numerator. I can't just assume I'll get a 0. I need to show that I have 0 over 0 to apply L'Hopital's rule. L'Hopital's rule is very specific. I've got to have that ratio indeterminate. So if my numerator turns out to be 1 or -3, I cannot apply L'Hopital's rule, and I'll have to go back and maybe try an old strategy. All right, let's just see what happens. Sine of 2 pi, that's the same thing as sine of 0, which we already said is 0. So 2 pi times 0, I'm going to get 0. Okay, cool. 2 pi squared, well, 2 squared is 4, and pi squared is pi squared. So I've got 4 pi squared minus 4 pi squared. Okay, I think I'm happy. The numerator is going to 0. The denominator is 0. So this is prime and ready for L'Hopital's rule. That's a ratio indeterminate, meaning that limit up above will be equal to another limit applying L'Hopital's rule, H for L'Hopital's rule. And I'm going to take the derivative of the numerator separate from the denominator. And this one, the denominator looks much easier to find. It's just the old derivative power rule. 2 pi is a constant, so the derivative is going to go to 0. The derivative of 1x is 1. Now, top, it's a different story. I start off with a product. So the derivative of the product, x times sine, I'm going to be applying the product rule for derivatives. The first times the derivative of the second function. The derivative of sine, we said earlier, was cosine. plus the second function times the derivative of the first. The derivative of 1x is 1. The derivative of x squared will be 2x. And, well, 4 pi squared is just some number, so the derivative goes to 0. Okay, I'm going to clean it up a bit. Looks like we have x cosine x plus sine x plus 2x. I think I did a bad thing and dropped my limit notation. That's really bad. I harp on my students hardcore, but this is still a limit as x approaches 2 pi. This is still a limit as x approaches 2 pi. Oh gosh, don't make that mistake. All right, but L'Hopital's rule is still another limit. So I simplify it, make it pretty, and I think I'm ready for direct substitution now. So now I can drop the limit notation. I'm going to direct substitute 2 pi into all of these x variables. So I have 2 pi times cosine 2 pi plus sine of 2 pi plus twice 2 pi. 2 pi is coterminal to 0 on the unit circle. Cosine of 2 pi is positive 1. Sine of 2 pi is 0. Double 2 pi, you get 4 pi. So I believe my limit should be 2 pi plus 4 pi, or 6 pi altogether. All right, so the limit as x approaches 2 pi of this function is approaching 6 pi. L'Hopital's rule says that means the limit of my original function is also approaching 6 pi. All right, those two examples were ratio indeterminants. Let's see what happens when we direct substitute and we get maybe a difference indeterminate. Let's take a look at this next example. The limit as, let's say, I like this one. X approaches 0 from the right of 1 over x minus 1 over e to the x minus 1. All right, I've got this function, 1 over x minus 1 over e to the x minus 1, and I want to know what's happening as x approaches 0 from the right. So is it going to infinity, diverging? Is it going to go to a number, L, so I can say the limit is a number? What's going on? I think I'll try direct substitution. Plugging in 0. So I have 1 over 0 from the right minus 1 over e to the 0 minus 1. From the right, just try to think of like visually what's going on. So as I approach 0 from the right, we're talking about super small positive numbers. So 0.0001, 0.00001, like small positive numbers. So that's some thing I don't quite know. This is something I don't quite know. Oh yeah, now we've talked about this earlier. 1 divided by the smallest positive number you can think of. With the understanding of limits, this is basically going to positive infinity. Same thing's true here. E to the 0 power, well, that's going to be 1. Let me kind of fix this up. Any non-zero number raised to the 0 power will be 1. So down here in the denominator, I have 1 minus 1. 1 minus 1 is going to 0. So I have 1 minus 0 again. And again, I've got that idea of these are positive values down there. So this is skyrocketing very quickly up to infinity. And here I have a difference indeterminate. I was kind of hoping for a ratio indeterminate. Ratio means I can apply L'Hopital's rule. If I get a difference, that means I cannot. But what I can do is maybe go back to my function and see if I can maybe actually do the subtraction, somehow rewrite this function in such a way that when I do direct substitute, I do get a ratio indeterminate. So I see the giant minus sign, I see the two fractions. I think what I'm supposed to do is simply subtract these two fractions. When I do, I'll have a common denominator and something up top, so it'll be in that ratio format. So I'm going to go ahead and get a common denominator. So the first function needs the denominator e to the x minus 1. So I'm going to multiply by e to the x minus 1, top and bottom, just a form of 1. The second function needs that denominator of x. So I'm going to multiply by another form of 1, x over x. This will just get that common denominator. Oh, those ones make this multiplication step easy. One times anything is that anything. Down below, I'll just keep it as x times e to the x minus 1. Though, thinking about it now, maybe I want to distribute it. That's okay though. I'm going to multiply at the top, keep my denominator factored. Now they have a common denominator, so I'm able to do the subtraction. I'm still just cleaning up this limit, rewriting it. So my numerator has three terms: e to the x, a negative 1, and a negative x. Now because I am about to take the derivative of the numerator separately from the denominator, right now that's a product, which I think is okay. If I were to distribute, I would still have a product. Okay, never mind. I'm just going to leave the denominator as is. All right, now I've rewritten my limit, and I think if I try direct substitution now, at least it looks like a ratio, so hopefully it'll be that one of those ratio indeterminants. So in this format, I'm going to try direct substitution again. I'm secretly hoping this thing just becomes 1/6. I'll be done with the problem. All right, let's plug in zeros. E to the 0 power is 1, so in the numerator I have 1 minus 1 is 0. Down below, same thing, e to the 0 is 1, 1 minus 1 is 0, 0 times 0, I'm sure hoping is 0. Bam, I got this ratio indeterminate. That means I could not apply L'Hopital's rule to my original function, but rewriting it as such, I can apply L'Hopital's rule to this form of that original function. So I'm now ready to apply L'Hopital's rule to this. So, notation-wise, I'm going to say is equal to h to represent I'm applying L'Hopital's rule. I'm not going to forget my limit notation. L'Hopital's rule says the limit of this function will be equal to another limit of a different function, where that different function is the derivative of the numerator over, separately, the derivative of the denominator. Up top looks really easy. The derivative of e to the x is e to the x. The derivative of constant goes to 0, and the derivative of negative x is negative 1. Down below, I do have a product, so I'm going to apply the product rule for derivatives. Okay, first, times the derivative of the second. Well, the derivative of e to the x minus 1 will be e to the x. Plus the second function, e to the x minus 1, times the derivative of the first, 1. Clean this up a bit. Numerator looks nice, e to the x minus 1 all over. Down below, I guess I'll just keep it like that. X times e to the x plus e to the x minus 1. Some of you may want to do some sort of reduction. That's not possible because of the plus sign. Okay, so I'm now going to try direct substitution and kind of hope this thing spits out a number. So I have e to the 0 minus 1 over 0 times e to the 0 plus e to the 0 minus 1. Okay, up top I've got 1 minus 1 is 0. Down below, 1 times 0 is 0, plus 1 minus 1, oh my gosh, 0 and 0. Well, guess what? That is a ratio indeterminate. L'Hopital says I can apply L'Hopital's rule to this function, and that limit will be equal to another limit. Okay, so I'm going to apply L'Hopital's rule a second time. I'm applying L'Hopital's rule. It's equal to another limit, where I take the derivative of the numerator separate from the derivative of the denominator. Up top, I think it's easy. The derivative of e to the x minus 1 is e to the x. Down below, I've got a product and an exponential. The constant will go away. This product does look a little bit simpler. First times the derivative of the second plus the second times the derivative of the first, which is 1. The derivative of this e to the x is e to the x, and the minus 1 goes away. So I've got e to the x in the numerator. In the denominator, I have x e to the x plus e to the x plus e to the x. That's just 2, oh wait, is that right? That should be gone. Let's see. Oh no, that's right, yeah. So then I've got just 2 e to the x. Before I try direct substitution, hopefully you remember this back from limits earlier in the semester, you try to clean them up as much as possible. So I see a lot of e to the x's. I'm going to factor 1 from the denominator. I'm going to pretend like I don't know those add to. So I'm going to say, if I take out a e to the x from all 3 terms in the denominator, I'll have x plus 1 plus 1. By factoring out the e to the x in the denominator, I can see I've got one top and bottom. Those are going to reduce or divide to 1. The e to the x problem is gone in the numerator. I'm going to rewrite my limit. So up top I have just 1. Down below I have x plus 2. Well, that's pretty. All right, try direct substitution again. Yay! I just got the number 1/2. That means if I were to take a look at this function's graph, as x approaches 0 from the right, this function is approaching 1/2. L'Hopital's rule says that this function will also be approaching 1/2. L'Hopital's rule says this original function will also be approaching 1/2. All right, so L'Hopital's rule, you may have to apply it more than once. If I had not simplified the e to the x in this step, I would have just been kind of continuing going over and over again with those e to the x's. So always try and simplify before you direct substitute. So once you take the derivatives, factor things out like we were used to with limits and derivatives, factor and try to simplify as much as possible. Then you can direct substitute, and hopefully you'll get a ratio indeterminate that you can play with. Let's do one more example. I have not done a product yet, so let's see what happens with that. All right, let's take the limit, evaluate the limit. As x approaches 1 from the left of the product 1 minus x and tangent of pi x over 2. All right, I've got some function, some weird form of tangent, and I want to know what's going on this function as I approach 1 from the left. Okay, just like any limit, I'm going to try direct substitution. If I get a number, I'm done. So I have 1 minus 1 times tangent of pi halves. And I'm under the, visually I'm just kind of thinking I'm coming from the left. Okay, but this is, I think I know what's going on here. So 1 minus 1, that's just going to be going to 0. Tangent of pi halves, it's undefined, but from the left. So let me just draw a picture of tangent real quick. Let's get my mind wrapped around what's going on. And tangent of 0 is 0. Tangent of pi fourths jumps up to 1. Tangent of pi halves is undefined. We have this vertical asymptote. So tangent's kind of doing this. Does something similar over there, something similar over here. So tangent of pi halves is undefined, but as I approach pi halves from the left, just like from the left at least, tangent of pi halves will be going up toward positive infinity. It wouldn't matter if it was negative infinity or positive infinity. I just need that product situation. So again though, we have 0 times this infinity, and we're not sure quite how to handle that. So what I'm going to do is take my function and hopefully, like the difference, I can rewrite it to look like a ratio. Products, well that should be easier to manipulate. I could go back to my original function, and I got two options really. That first factor, I could kick it down to the denominator if I raise it to a negative first power. And then tangent itself has a reciprocal function, cotangent. So I could simply move that down to the denominator as long as I call that argument like a cotangent of that stuff. So I think I'll do that. I'm just going to reciprocate tangent. So I'm rewriting my original function. I still have a limit as x approaches 1 from the left of, I'm leaving 1 minus x alone. And I'm going to rewrite tangent as cotangent of pi x over 2. Rewriting. I was given a product, I'm rewriting it as a ratio. Hopefully now when I direct substitute, I get out a ratio indeterminate. Plugging in 1. 1 minus 1 over cotangent of pi halves. Well, tangent of pi halves is undefined. You could think of that as 1 divided by 0, the y value divided by the x value. So cotangent is simply the reciprocal x over y, or 0 in this case. So cotangent of pi halves is 0. And lo and behold, thank goodness, I've got a ratio indeterminate, meaning I can apply L'Hopital's rule to this form of that function. Not the original, but this ratio form. L'Hopital's rule says it's equal to another limit as x approaches that same value. And you now take the derivative of the numerator, -1, separately from the derivative of the denominator. The derivative of cotangent of a function will be negative cosecant squared of that function, and then if I need to apply a chain, you take the derivative of that inside. So I've got cotangent of pi halves x, so that's going to be a negative cosecant squared of pi x halved times a chain. The derivative of the inside, well, the derivative of a number x is simply that coefficient. So this is just times pi over 2. I just said, after you take these derivatives, you simplify first before you try to do direct substitution. So I see some simplifications. A negative divided by a negative will become positive. If you have this thing being multiplied by pi over 2, then I have all of that over 2. So I've got 1 divided by a fraction, the 2 in the denominator. You can think of a keep, change, flip, but that 2 is going to eventually join the numerator position. So I'm going to clean this up. I don't know why I have this symbol there. That's just 1 from the left. I don't know why I wrote -1. All right, the limit as x approaches 1 from the left of, that's now going to be positive 2 over cosecant squared of pi x over 2. I should probably put the pi out front, but times pi. Again, negative divided by negative is positive, and then if you take a fraction divided by 2, that 2 goes up top. Or, you got it. Okay, so now I think I'm ready for direct substitution. Plugging in 1, I just have in the denominator cosecant squared of pi halves times 1, then times pi. So I just need cosecant squared of pi halves. So kind of the way I think about this, I know sine of pi halves is 1, so then cosecant of pi halves is the reciprocal 1 over 1, which is just 1, and then cosecant squared of pi halves is simply that value, 1 being squared, and 1 squared is still 1. That's just 1. So I have 2 over 1 pi, or 2 over pi. The limit of this function here, that ratio, is 2 over pi. So L'Hopital says the original function is also 2 over pi. All right, I hope that helps. In the next video, we'll do very similar situations, but we'll talk about the power indeterminants. See you next time.